Something impossible has just been confirmed in the deep reaches of our universe. For years, astronomers have stared at the images returned by the James Webb Space Telescope, puzzled by a specific set of anomalies. Tiny, unassuming specks of red light scattered across the distinct background of the cosmic dawn. They looked like faint, distant galaxies, or perhaps dust-shrouded stars, easy to overlook in the grand tapestry of the cosmos. But a groundbreaking analysis released in January 2026 has shattered that assumption. We now know that one of these specks, an object catalogued as Canis LRDZ 8.6, is not a galaxy, and it is certainly not a normal star. It is a monster. We are looking at a celestial hybrid that was previously only a mathematical nightmare, a colossal object known as a quasi-star. This is an object with the mass of 1 billion suns, but here's the terrifying twist. The heart of this star is not made of nuclear fusion. The heart of this star is a supermassive black hole. We are witnessing a black hole wearing a star like a suit of armor, devouring it from the inside out, and in the process, solving one of the greatest paradoxes in the history of astrophysics. What you are about to hear is the story of how a single red dot has rewritten the history of the early universe. It forces us to ask a disturbing question. Were the first monsters of the cosmos born, or were they made? And if black holes can grow inside stars, what does that mean for the galaxy you are living in right now? To understand the magnitude of this discovery, we have to peel back the layers of this cosmic Russian doll, starting with the image that started it all. When the James Webb Space Telescope first turned its golden mirrors toward the edge of time, it began picking up these little red dots, or LRDs. In the astronomical community, the name is deceptively cute. These objects appear compact, extremely bright in the infrared spectrum, and remarkably numerous. At first glance, the data suggested they were active galactic nuclei, supermassive black holes feeding in the centers of baby galaxies. But there was a problem. The math did not add up. The light coming from these objects was too red, too compact, and strangely lacking the specific X-ray signatures we usually associate with exposed quasars. They sat in an uncanny valley of data, defying classification. Then came the observation of Canis LRDZ 8.6. Located at a redshift of 8.6, which places it just 570 million years after the Big Bang, this object represents a time when the universe was still wiping the sleep from its eyes, emerging from the cosmic dark ages. In January 2026, astronomers from the Center for Astrophysics, led by researchers analyzing deep field spectroscopy, managed to pierce the veil of this object. What they found was a spectrum that looked like a contradiction. It showed signs of a supermassive black hole, broad emission lines that indicate gas swirling at terrifying speeds. But it also showed a thermal curve, a temperature profile that looked like a star that was far too big to exist. This brings us to the core of the mystery. In standard astrophysics, a star is a delicate balance. Gravity tries to crush the star inward, and nuclear fusion in the core pushes outward, creating a state called hydrostatic equilibrium. But there is a limit to how big a star can get. If a star becomes too massive, say a few hundred times the mass of our Sun, the radiation pressure becomes so intense that it blows the star apart. This is known as the Eddington limit. However, the object identified in the new data defies this limit. It is stable, yet it possesses a mass that shouldn't be possible. The only way to explain this, the only model that fits the terrifying data we are seeing, is the quasi-star hypothesis. Imagine a cloud of pristine gas in the early universe, a cloud so massive that it collapses under its own weight. Usually this cloud would fragment into hundreds of smaller stars, but in the unique conditions of the early cosmos, where heavy elements were scarce and gas cooling was inefficient, the cloud collapses directly. The core becomes so dense, so heavy, that it does not ignite fusion in the traditional sense. Instead, the core collapses directly into a black hole. But here is the key. The outer layers of the gas cloud are so massive that the explosion that usually announces the birth of a black hole, the supernova, is smothered. The explosion is choked by the sheer weight of the surrounding gas. So what you are left with is a black hole, perhaps 10 or 20 solar masses to start, trapped inside a gigantic envelope of hydrogen gas that extends for astronomical units. This is the Quasi-Star. It is a star powered not by fusing hydrogen into helium, but by feeding its own heart to the black hole within. The energy radiating from the surface, the light that traveled 13 billion years to reach the mirrors of the James Webb Space Telescope, comes from the friction and violence of gas falling into the event horizon deep inside the star. Before we go further into the mechanics of this devouring process and what it tells us about the impossible size of modern black holes, this is the perfect moment to ensure you do not miss the updates on this rapidly evolving story. We are dissecting new papers from the Center for Astrophysics as they are published. If you want to stay ahead of the curve on cosmology and astrophysics, make sure you are subscribed to the channel. We go deep into the data here, and you will not want to miss the breakdown of the next target in the survey. Now let us analyze the mechanics of this beast. Why is the confirmation of a quasi-star in 2026 such a pivotal moment? It solves the too big, too early problem. For decades, cosmologists have struggled with a mathematical impossibility. When we look at the universe as it appeared less than 1 billion years after the Big Bang, we see supermassive black holes with masses billions of times that of the Sun. This should not be possible. Black holes grow by eating matter, a process called accretion, but accretion takes time. There is a speed limit to how fast a black hole can eat, governed again by that Eddington limit. If it eats too fast, the radiation pushes the food away. If you start with a small black hole, the kind formed by a normal dying star, there simply is not enough time in 500 million years to grow into a billion solar mass monster. You can leave the black hole feast running 24 hours a day, 7 days a week, and the math still falls short. It is like trying to fill an ocean with a teaspoon. But the quasi-star flips the table on this constraint. Because the black hole is buried deep inside this massive envelope of gas, the radiation pressure that usually stops the feeding is contained. The envelope acts like a pressure cooker. The energy pushes against the gas, puffing the star up to the size of a solar system. But the weight of that billion solar mass envelope keeps force-feeding the black hole at the center. In this scenario, the black hole is not limited by the standard accretion rates. It can grow at super Eddington rates, gorging itself on the surrounding star. It can grow from 10 solar masses to 10,000 or even 1,000,000 solar masses in a fraction of the time it would take a naked black hole. This is the direct collapse scenario in action. The little red dot known as CANUCS-LRD-Z-8.6 is the smoking gun. It captures a moment in cosmic history where the black hole is effectively wearing the star as a disguise, growing fat on the stellar material until it eventually consumes the entire envelope. The data provided by the researchers, including prominent figures like Fabio Pacucci, utilizes the near-infrared spectrograph on the Webb telescope to dissect the light from this object. What they found was a specific signature in the hydrogen alpha lines, a fingerprint of light that reveals the velocity of the gas. The lines were broad, indicating gas moving at thousands of kilometers per second, which is a telltale sign of a deep gravitational well, a black hole. But overlaid on this was a continuum of light that suggested a surface temperature much cooler than an accretion disk, something closer to a supergiant star. This duality is exactly what the models predicted for a quasi-star. The implications of this are staggering. It suggests that the supermassive black holes we see today, the anchor of our own Milky Way, Sagittarius A star, and the monsters in the center of M87, did not start as small stellar remnants. They were likely born as these heavy seeds. They were born big. The universe did not build its monsters brick by brick. It forged them in massive, direct collapse events during the cosmic dawn. The little red dots are the baby photos of these titans. We need to consider the environment where this happens. The universe at redshift 8.6 was a very different place. It was denser, hotter, and filled with turbulent currents of pristine hydrogen and helium. The heavy seed theory requires these massive clouds to remain pure, without the cooling effects of heavy metals like carbon or oxygen, which would cause the cloud to fragment into smaller stars. The conformation of this object suggests that pockets of this pristine gas survived longer than we thought, or that dynamic heating in the early universe prevented fragmentation, allowing these monster stars to form. Let us look deeper into the Russian doll analogy, because the physics there is fascinating. Inside the quasi-star, the black hole is surrounded by an accretion disk, just like a normal quasar. But instead of that disk venting its fury into open space, it vents it into the stellar plasma. This energy heats the envelope, keeping it inflated. It is a precarious balance. The black hole is a parasite, keeping its host alive just long enough to consume it. As the black hole grows, the star expands and cools, becoming redder. This explains why JWST sees them as little red dots. They are red because they are cool supergiants, and they are dots because they are incredibly distant. But their luminosity is off the charts, thousands of times brighter than they should be for their temperature. The research released in January 2026 highlights another critical aspect: the spin. The spectra indicate that the material falling into the black hole is doing so with tremendous angular momentum. In a normal star collapse, angular momentum can tear the star apart or halt the collapse. But in a quasi-star, the envelope is so large that it can absorb and redistribute this angular momentum, allowing the core to feed unobstructed. It is a perfect storm of conditions, designed to manufacture supermassive black holes. This discovery also challenges our understanding of galaxy formation. The old model was that a galaxy forms first, a cloud of gas comes together, stars turn on, and eventually, a black hole forms in the center and grows slowly. The quasi-star model suggests a co-evolution, or even a black hole first scenario. These massive objects could have acted as the gravitational anchors around which the first galaxies coalesced. The black hole was not a late addition to the party, it was the host. To detect the presence of elements heavier than hydrogen and helium. The James Webb Space Telescope allows us to detect the presence of elements heavier than helium. In the spectra of CANUCS-LRD-Z-8.6, the researchers looked for the pollution of metals. A standard supermassive black hole at this epoch should have already enriched its surroundings with metals from previous generations of supernovae. However, the data hints at a surprisingly metal-poor environment for the mass of the object. This aligns perfectly with the direct collapse theory. This object formed from a pristine cloud, bypassing the cycles of stellar evolution that create heavy metals. Let us pause to visualize the scale here. A quasi-star would be larger than our entire solar system. If you place the Sun next to it, the Sun would be a microscopic grain of sand against a beach ball. The photosphere, the surface we see, is tenuous and diffuse, glowing with a deep, sullen red light. But if you could travel inside, past the layers of hydrogen plasma, the temperature would skyrocket. You would descend through 1 billion miles of gas, the pressure mounting, until you reached the storm at the center, a glowing, screaming accretion disk swirling around a black hole that is already thousands of times more massive than our Sun. It is a hellscape hidden inside a distinct, calm red shell. Means that when we look at the deep fields, those thousands of little red dots are likely a population of these monsters. We are seeing a phase of the universe we did not know existed, the era of the black hole stars. This transitional phase is short-lived in cosmic terms, perhaps only lasting a few million years. The black hole eventually wins. The envelope is consumed or blown away, and the naked quasar is revealed. This explains why we see so many quasars slightly later in the universe's history. They are the skeletons left behind after the quasi-stars have died. But what happens to the gas that gets blown away? The death of a quasi-star is not a silent event. As the black hole becomes dominant, the radiation pressure eventually overcomes the gravity of the envelope. The outer layers are ejected in a violent wind, enriching the surrounding intergalactic medium. This wind could be the trigger for star formation in the surrounding neighborhood, kick-starting the birth of a galaxy. So, these monsters are also creators. They clear out the fog of the early universe and set the stage for the structured cosmos we see today. The little red dot mystery also forces us to reevaluate our instruments. We thought we knew what a black hole looked like. We thought we knew what a galaxy looked like. But these objects mimicked both while being neither. It is a lesson in the dangers of interpretation. Until the spectroscopic data from the NIR SPEC instrument came in, we were just guessing based on colors. The spectrum is the DNA, and it revealed a chimera. There is a fascinating angle regarding the seed mass. In astrophysics, the seed is the starting mass of a black hole. Light seeds are the remnants of the first stars, maybe 10 to 100 solar masses. Heavy seeds are these direct collapse black holes, starting at 10,000 to 100,000 solar masses. The existence of Canix LRDZ 8.6 at redshift 8.6 effectively puts a nail in the coffin of the light seed-only theory for supermassive black holes. There is simply no way to get from a light seed to the billion solar mass beasts we see so early without breaking the laws of physics. The heavy seed is the necessary solution, and the quasi-star is the factory that produces them. Let us speculate on the future of this research. With this confirmation, the James Webb Space Telescope will likely target more of these little red dots for deep spectroscopy. We need to know if this is a common pathway or a rare anomaly. Did every supermassive black hole start this way? Did the black hole at the center of the Milky Way once reside inside a quasi-star? It is a tantalizing possibility. It connects our local reality to these distant, ancient lights. The narrative of cosmic dawn is being rewritten from a slow, gradual awakening to a violent, rapid explosion of growth. The universe did not tiptoe into existence. It roared. These quasi-stars represent a mode of growth that is catastrophic and efficient. They are engines of mass accumulation that operate on a scale we can barely comprehend. Furthermore, this discovery ties into the concept of obscured growth. For a long time, astronomers suspected that a lot of black hole growth was hidden behind dust, but in the case of LRDs, the black hole is not hidden by external dust. It is hidden by the star itself. The dust is the fuel. This distinction is crucial because it changes how we calculate the total energy budget of the early universe. If thousands of these objects exist, they contributed a significant amount of ionizing radiation to the cosmos, perhaps playing a role in the epoch of reionization, when the neutral fog of the universe was burned away. The physics of the envelope also presents a challenge to fluid dynamics simulations. How does a star maintain integrity when its core is being eaten? The energy transport mechanisms must be incredibly efficient. We are talking about convection currents that move mass and energy across distances of billions of kilometers. The turbulence in these layers would be unimaginable. Computer models running on the world's most powerful supercomputers are only now beginning to replicate the stability of these objects, and the observations from 2026 provide the critical boundary conditions needed to fine-tune those simulations. There is also the question of the Goldilocks zone for these objects. They can only form in halos of dark matter that are just the right size, too small, and the gas doesn't collapse fast enough, too big, and the gas fragments. This ties the formation of quasi-stars to the elusive nature of dark matter itself. The distribution of little red dots might essentially map the distribution of dark matter halos in the early universe, giving us a new tool to probe the invisible scaffolding of the cosmos. As we move deeper into the analysis of Canix LRDZ 8.6, we must consider the perspective of time. We are seeing this object as it was over 13 billion years ago. It is gone now. The star is long dead, the envelope consumed. The black hole that was born inside it has likely grown, merged with others, and now sits in the center of a massive elliptical galaxy, dormant and dark. We are looking at a ghost, but this ghost tells us how the giants of today were born. The implications for the standard model of cosmology are subtle but profound. We do not need to invent new physics to explain these objects. General relativity and thermodynamics are sufficient, but we do need to apply them in extreme configurations. It is a triumph of theory meeting observation. Decades ago, theorists proposed the existence of quasi-stars, or frozen stars, or black hole stars, as mathematical curiosities. To see one confirmed in the data is the ultimate validation of the scientific method. We predicted a monster, and then we found it. This brings us back to the sheer visual wonder of it. If you were floating in space near one of these objects, it would not look like a star in our night sky. It would dominate your view, a wall of angry red fire. And if you had eyes that could see X-rays, you would see the piercing beam of the central black hole trying to punch through, making the whole star glow with an eerie inner light. It is a spectacle of destruction and creation, bound together. As we approach the final understanding of these phenomena, think about the caterpillar and the butterfly, but add a twist of cosmic horror. The caterpillar, the gas cloud, builds a chrysalis, the quasi-star. Inside, a transformation happens. But instead of a butterfly emerging, a dragon is born. The black hole is the dragon. It consumes the chrysalis and emerges as a quasar, one of the brightest and most powerful objects in the universe. We have finally caught the universe in the act of this metamorphosis. If you find the revelation of these cosmic monsters as fascinating as we do, and if you want to support content that prioritizes deep, technical breakdowns of the latest scientific news, please hit that like button. It helps the algorithm understand that there is an audience for intelligence and curiosity. We are standing at a precipice of understanding. The little red dots, once thought to be background noise, Sautor, have turned out to be the main characters of the early universe. They are the missing link between the primordial gas and the structured galaxies we inhabit. The mystery of the early supermassive black holes is no longer a contradiction. It is a story of a star with a dark heart. As the James Webb Space Telescope continues its survey, and as the next generation of telescopes comes online, we will likely find more of these beasts. We will map their population, measure their growth, and understand the role they played in sculpting the cosmos. But for now, we can marvel at the fact that in January 2026, the universe became a little less mysterious and a lot more terrifying. The dots are not just dots, they are the crucibles of the giants.